Salam, peace be upon you. My name is Mohammed Layiq Sediqi, the father of Holophase. Part 32. Action-like Semantic Principles. Remember the language we are learning together. There is one field, phi, the holophase, one continuous cyclic movement from which all of reality unfolds. When phi begins to change, its first derivatives appear, and with them three dimensions reveal themselves at once: time as omega, space as k, and motion as v, built from both. Every higher derivative is a finer and more refined question about how phi is changing, and each one casts three shadows together: a time shadow, a space shadow, and a motion shadow. These echoes mix and weave into one another, forming the patterns we call fields, particles, bodies, thoughts, and worlds. In this picture, everything that exists is a living tapestry of phi, endlessly echoing through its derivatives and their dimensional shadows. And today, in this part, we pause again to listen carefully to just one of those echoes. Our journey through the quadratic semantics of the holophase has brought us to a great height. We have learned how to measure the intensity of change through omega squared, and the intensity of spatial variation through the magnitude of k squared, written as k squared. We have seen how these intensities combine and balance in local trade-offs, such as the Lagrangian-like density given by omega squared minus k squared. Now we take the ultimate step. We move from the local to the global, from a momentary negotiation at each point to the judgment of an entire history. Today we encounter the supreme semantic principle that appears to govern the unfolding of the entire story of motion. We explore what I will call action-like semantic principles. This is the level where the holophase language reveals its deepest and most elegant form of grammar, a principle of global optimization that selects from all possible stories the one that actually gets told. 1. The global judge, from local balance to whole history assessment. Think first about a local balance, such as the Lagrangian density. It gives us a kind of local cost or local score for how phi is changing at a single point in space and time. You can imagine it as judging the quality of a single word or a single phrase in a sentence. But a masterpiece is not judged by the quality of just one word. It is judged as a whole. In the same way, the universe does not decide its behavior based only on an isolated instant. What matters is the entire path, the entire configuration through space and time. So how do we judge an entire story, the entire pattern of phi across a region of space and over a duration of time? We integrate. We sum, or average, all those local scores over the entire domain of interest. This total sum, the integral of the local balance density over space and time, is what we call the action. In words, the action is the integrated total of the local cost of a pattern over its whole space-time domain. It is a number we associate with an entire possible story. It is not a number we ordinarily measure directly. Instead, it is a number we can calculate for any possible way phi might unfold between some chosen starting state and some chosen ending state. Now comes the breathtaking principle. Of all the infinitely many possible stories that could connect a given beginning to a given end, the story that actually occurs in reality, the one we observe, is the one for which this total action is stationary. Stationary here means that if you make a tiny variation in the story, a tiny change in the path, the total action does not change to first order. It is at a kind of plateau, which may be a minimum, a maximum, or a saddle point, although for many familiar systems it is effectively a minimum. This is the principle of stationary action, often referred to as the principle of least action. 2. The analogy. The scenic path versus the direct path. To make this more intuitive, imagine you are standing on a hillside at point A, and you need to roll a ball down to point B at the bottom. There are infinitely many possible paths the ball could take: a straight diagonal, a wide curve, a wiggling zigzag, or something in between. Each path has an associated total cost, depending on what we decide cost means. It could be total time taken, total distance, or a more subtle combination such as the integrated difference between kinetic and potential energy. The principle of least action says, in spirit, that the ball will roll along the path that makes this special total cost optimal, often minimal. But the crucial subtlety is that this cost is usually not just time or distance alone. For the ball, the relevant quantity is a balance between kinetic energy, which prefers rapid motion, and potential energy, which depends on height in the gravitational field. The action principle does not simply pick the shortest distance between A and B, nor does it simply pick the path that gets there in the absolute least time if you consider arbitrary shapes and constraints. It picks the path that gives the best overall compromise when you integrate this special balance, kinetic minus potential, over the entire motion. For a simple ball thrown under gravity with no air resistance, that optimal path turns out to be a parabola, exactly what we observe in real life. So the action principle does not just pick the shortest or the quickest in a naive sense. It picks the most optimal path according to a sophisticated blended criterion. Nature chooses a kind of scenic route that is also efficient, one that balances competing tendencies in the most elegant way. 3. Action as global sentence quality. In the holophase language, we can think of the action as the ultimate quality measure for an entire sentence or paragraph of reality. At the base level, the derivatives, omega, k, and other quantities, play the role of letters. The local balances, such as omega squared minus the magnitude of k squared, are like local grammatical assessments of words or short phrases. They tell us whether a configuration at a point is energetically efficient, overstressed, or balanced. When we integrate such a balance over space and time to get the action, we obtain something like the overall elegance, conciseness, or good form of the entire sentence that describes a happening. The principle of stationary action then acts as a kind of cosmic editorial rule. It says that when the universe tells a story from beginning to end, it uses the sentence structure that is optimally formed, the one that, in total, strikes the best possible balance between temporal activity and spatial structure. From this single global editorial rule, something remarkable occurs. All the detailed local grammatical rules, which we know as the equations of motion, fall out automatically when we apply the mathematics of variation. The power. One principle, many equations. This is the immense power and beauty of the action principle. Instead of writing separate laws for every phenomenon one by one, you can adopt a unified strategy. First, you choose the appropriate local balance, often called the Lagrangian density, for the field or system you're interested in. For a simple free field, that might look like omega squared minus c squared times the magnitude of k squared. For a particle moving in a gravitational field, it might look like kinetic intensity minus potential intensity. Second, you integrate this local balance over space and time to form the action associated with any candidate history. Third, you demand that the action be stationary with respect to any small change in that history. When you apply the calculus of variations, this demand produces the precise differential equations that the field or the particle must satisfy at every point in space and time. In other words, from the global editorial rule, the story must have stationary action, you derive all the local grammatical rules that the story must obey. The wave equation, Newton's second law, Maxwell's equations, Einstein's field equations, and many other fundamental dynamical laws can all be obtained in this way, by starting from their particular action. The action principle serves as a unified grammatical source code for dynamics. Phi. Dimensional expression, the judgment of wholeness. The action principle integrates over time, over space, and over motion. It therefore makes a deep statement about all three echoes of the holophase language. In the time echo, the action principle is teleological in a purely mathematical sense. It evaluates an entire history from start to finish. It does not say, the present force alone dictates the next instant, in the way we often tell the story in elementary physics. Instead, it says, given the boundary conditions at the beginning and end, The path that is realized is the one that makes the total action stationary. This is why, at the level of equations, many physical laws are time reversal symmetric. The equations themselves do not inherently prefer one direction of time. The action is computed over an entire history, and the same criterion can, in many systems, be applied to the reverse path as well. In the space echo, the action integrates over entire spatial regions. For continuous fields, this means that the principle selects spatial configurations that are optimal as wholes, not just point by point. Phenomena such as the shape taken by a soap film stretched across a wireframe, a minimal surface, are instances in which the spatial configuration minimizes an integrated quantity related to surface energy. In the motion echo, the action principle unifies time and space into a single space-time picture. A trajectory is not just a sequence of positions in time, it is a single continuous curve in space-time, a world line. The action is computed along this world line, and the principle selects the world line that optimizes the action. The velocity and acceleration at each moment are not primary ingredients. They are consequences of this world line being globally optimal. You can think of motion as the local footprint of a choice that has been made at the level of entire paths. 6. Position in the master tree, the apex of quadratic semantics. Within the holophase language tree, the principle of stationary action sits at the very top of the quadratic, balance, and action semantics tower. It is the crowning apex of this whole structure. It synthesizes everything beneath it. It is built from the intensity measures like omega squared and the magnitude of k squared. It uses the combined balances such as omega squared minus the magnitude of k squared as its integrand, and it embodies the grammar of optimization and selection. This principle is more than just another node. It is the generative rule for the entire dynamical side of the tree. It is the meta rule that tells us how the letters and words of the file language must be combined to form valid physical sentences, sentences that are actually realized as the world. From this highest vantage point, we can look down and see how the entire semantic structure of dynamics flows from the single cyclic movement of phi, shaped and constrained by intensity measures, balances, and finally by this global selection principle. 7. Relations to neighboring branches. The action principle is intimately connected to its neighboring branches in the master tree. It leans directly on the combined balances we explored earlier, such as omega squared minus the magnitude of k squared. Those balances are the integrand, the local density that we integrate. The action is the integral of that density over a region. Dispersion relations, which tell us how omega depends on k for waves, can often be derived from an action principle by assuming a wave-like form for the field and then demanding stationarity. The familiar relation omega equals c times the magnitude of k for light in a vacuum, for instance, emerges as a consequence of stationarity for an appropriate field action. The usual notion of energy and conservation laws also emerges from the action principle through a result known as Noether's theorem. This theorem states that for every continuous symmetry of the action, there is a corresponding conserved quantity. If the action is invariant under shifts in time, energy is conserved. If the action is invariant under shifts in space, momentum is conserved. This means that conservation of energy is not a separate axiom. It is a consequence of the symmetry of the action. In the holophase interpretation, the energy tally is a particular weighted sum of derivative intensities that remains conserved because the action respects time translation symmetry. Topological semantics also interacts with the action principle. Many topologically stable configurations, such as solitons or certain kinds of defects, are solutions that minimize or extremize the action within a particular topological class of configurations. Their stability is directly tied to being locally or globally action optimal under the allowed variations. Finally, wave interference gains a deep reinterpretation when we move into quantum territory. In the path integral formulation of quantum mechanics, a particle is described as exploring all possible paths between 2 points. Each path contributes with a phase that depends on its action. Paths whose actions differ significantly tend to interfere destructively and cancel each other out. The classical path, the one that would be predicted by the ordinary least action principle, is precisely the path where the phases of nearby paths add constructively. So even quantum interference, at a deeper level, can be seen as resting on an extended action principle. 8. Semantic meaning, the grammar of elegant necessity. At the semantic level, the action principle represents the dimension of elegant necessity. It expresses the idea that the universe does not unfold in an arbitrary way, nor is it simply pushed by local mechanical forces in a blind sequence. Instead, it unfolds as if it were following a script written by an author who cares about the overall elegance, economy, and coherence of the story. The history that actually occurs is the one that is, in a precise mathematical sense, the most well-formed possibility among all alternatives consistent with the boundary conditions. This replaces the older metaphor of forces pushing things around with the metaphor of optimization and selection. A planet does not orbit the sun simply because it is being pushed and pulled at every instant by a gravitational force. In the action language, the elliptical orbit is the space-time path that minimizes, or more precisely makes stationary, the total action for that system. Light does not bend near a massive object because something tugs it sideways. It follows the path through curved spacetime that minimizes a certain action related to optical length. In the holophase language, this is the highest expression of grammatical coherence. It is the rule that ensures the story of phi is not just a random jumble of motions, but a meaningful, elegant, and, in a deep sense, necessary narrative. 9. Stability, variability, and falsifiability. The action principle also carries clear implications for stability, variability, and testability. A configuration or trajectory that truly minimizes the action, rather than just making it stationary in a neutral way, is dynamically stable. Small perturbations will raise the action, and the system will tend to return to the optimal path. This is the origin of many stability properties in mechanics and field theory. The specific form of the action is what varies from system to system. The action for light in a vacuum differs from the action for an electron in a magnetic field, and those differ again from the action for a vibrating string or a quantum field. This variability encodes the specific forces and interactions of each domain into a common grammatical framework. The differences between physical theories are largely differences in their choice of Lagrangian and action. The claim that dynamics is governed by a principle of stationary action is falsifiable. It would be overturned if we observe that the paths taken by isolated systems consistently and measurably deviate from any path that could be derived by minimizing or extremizing a reasonable local action integral. Classical mechanics provides one test. If you compute the action for all possible paths of a projectile between 2 points, and then find which path makes this action stationary, you obtain a parabolic trajectory. When you fire a projectile and account correctly for effects such as air resistance, the observed path matches the derived one remarkably well. In optics, Fermat's principle states that light takes the path of least time between 2 points, which is an action-like principle. This predicts the familiar laws of reflection and refraction. Experiments with lenses, mirrors, and prisms confirm these predictions with high precision. In electromagnetism and general relativity, the fundamental equations are derived from action principles and have been tested in countless experiments, from the behavior of circuits to the deflection of starlight by the sun and the timing of GPS satellite clocks. To falsify the action principle, we would need a clean, reproducible experiment where an isolated, fundamental system follows a path that cannot be described as a stationary point of any local action compatible with other observations. So far, no such exception is known. X. Appearance in nature. Optimization in plain sight. The action principle may sound abstract, but its fingerprints are visible almost everywhere in nature. The shape of a soap film spanning a wire loop is a direct example. The film adopts the surface that minimizes its total area, which is equivalent to minimizing a certain energy-related action. Without any conscious calculation, the film solves this optimization problem instantaneously. Another classic example is the brachistochrome problem, finding the curve down which a bead slides under gravity from one point to another in the least time. The answer is not a straight line, but a cycloid, a specific looping curve. When you build such a track and test it, the bead reaches the bottom faster along this cycloidal path than along any other smooth path connecting the same points. Planetary and satellite orbits are also optimized paths. The elliptical orbit emerges as the action optimal solution for a gravitational two-body problem. Engineers designing spacecraft burns are, in effect, working with these same principles. They adjust the spacecraft's path so that it lies on a trajectory that satisfies the appropriate action extremum for the combined gravitational environment and propulsion history. 11. Appearance in human and abstract life. The pattern of global optimization, of selecting entire paths or structures based on an integrated measure of quality, appears far beyond physics. It is a universal heuristic for intelligence and effective function. In decision-making and strategy, wise choices are rarely those that maximize only immediate gain. Good long-term planning evaluates entire trajectories of life or policy. You can think of this as a human-scale action principle. We intuitively weigh total cost and total benefit over long stretches of time, rather than only in the next moment. A similar thing happens in games such as chess. A strong player does not merely choose moves that look good in isolation. They evaluate entire sequences of moves, possible futures, and choose the line of play that leads to the strongest overall position. That is an action-like evaluation over a space of possible histories. In creativity and art, narrative structure in a novel or film is not just a sequence of isolated events. It is an arc that must make sense as a whole. Scenes are added, removed, or rearranged to improve the overall impact. This is editing as an optimization of a narrative action. A musical composition is shaped by similar considerations. A composer does not simply choose each note in isolation, but listens for the effect of whole phrases, sections, and the entire piece. The composition is right when, integrated over time, it has the desired balance of tension, release, contrast, and unity. In social and economic systems, policy is ideally designed to optimize a kind of social action, a measure of welfare or stability over long timescales and across populations. Short-term gains that lead to disastrous long-term costs are usually seen, in hindsight, as failures of this global optimization. Institutions and norms that survive across generations often do so because in practice they approximate solutions to difficult social optimization problems, minimizing various transaction costs and maximizing coordination. In learning and mastery, whether of a sport, an instrument, or a craft, practice gradually shapes an entire behavioral trajectory. Movements become smoother and more efficient, errors are eliminated, and the overall pattern becomes more elegant. This is your nervous system and body converging on paths in movement space that minimize unnecessary effort and maximize control. An embodied biological realization of an action-like optimization. 12. How to read the action principle in the world. You can train yourself to perceive the world not as a collection of things being pushed, but as a collection of optimal solutions to hidden problems. When you watch a river, its meandering is not random. Over geological time, the river tends to settle into a course that, given the terrain and sediment, minimizes a certain rate of energy dissipation. The river's shape is an answer to the question, how can water flow downhill in this landscape at the least long-term cost? When you watch animals move, such as a cat leaping to a high surface, you can see the same idea at play. The cat's trajectory and body posture are not arbitrary. They are shaped by evolution and learning to achieve a soft and accurate landing while minimizing wasted effort and risk. If you look at biological structures such as spiderwebs, honeycombs, or tree branches, you can see them as solutions to optimization problems. Maximize strength for a given amount of material. Maximize surface area for light capture, and so on. A simple hands-on practice is to take a piece of string, fix its two ends at points that are not directly above one another, and let it sag. The shape the string takes under gravity is called a catenary. It is not a parabola. It is the curve that minimizes the potential energy of the string. If you flip that curve upside down, you get the shape used in many suspension bridge cables. In your hands, you are holding a direct physical example of the action principle. The string chooses the curve of least energy, and it does so without any explicit computation. The physics itself is the computation. 13. Connection back to phi and the complete tree. Now we return once more to the one field, phi. The principle of stationary action shows us the ultimate consequence of phi being a single, coherent entity. If reality is built from one continuous field, then its unfolding story cannot be a random patchwork of unrelated local events. It must be globally coherent. The action principle is the grammatical rule that enforces this coherence. It is the mechanism by which an infinite space of possible phi patterns is narrowed down to the particular patterns that actually occur. From the silent, cyclic movement of phi, an entire language emerged. First, the alphabet of derivatives, then the local grammar of intensities and balances, and now the global editorial rule of action. This rule selects those stories, those histories of phi, that are so elegantly necessary that they become the world we experience. From this perspective, the laws of motion, the shapes of fields, and the patterns of waves are all expressions of phi's drive toward globally coherent, action-optimal behavior. We have now reached the conceptual summit of dynamics within the Holophase language. We can look back and see how everything we built, from letters to intensities to balances to global optimization, hangs together as one integrated semantic tower. Our next and final step in this episode will be to pause on this summit and look back across the landscape, gathering all these insights into a unified view. 14. Closing movement. The universe as an author of elegant necessity. As we close this exploration of action-like semantic principles, I invite you to hold a particular vision. The cosmos is not best described as a lifeless machine. It behaves much more like an author or a composer who is continuously writing an immense, multi-layered work and who follows a sublime rule. Tell the story that is, overall, the most elegantly formed. Every orbit of a planet, every ray of light bending around a star, every vibration of a string or membrane, every thought unfolding in your mind can be seen as a clause in this optimally formed story. You are not simply an observer watching a mechanical process. You are a living expression of this same principle of elegant necessity. Your own life trajectory, with all its choices and constraints, is shaped by countless optimizations. In your body, in your brain, in your environment. The feeling we sometimes have of rightness when we find a beautiful solution, the sense of inevitability in a well-played game, or the deep satisfaction we feel in a harmonious landscape or a well-crafted piece of music. All of these may be human reflections of a deeper fact, that we are recognizing in our own language the same kind of optimality that the universe realizes in its fundamental dynamics. You have now learned the name and nature of this principle within the Holophase story. You have seen how it runs like a golden thread from the simplest local measure of intensity to the highest global rule of selection. The next time you see a ball arc through the air, light reflect off a surface, or even feel the relief of finally making a difficult but wise decision, remember, you are witnessing, at different scales, the universe practicing its art. You are seeing the Holophase language speaking in its most refined and powerful dialect, the dialect of elegant necessity. Peace be upon you.